Lecture 6 on Mathematical Foundation of Robotics. In this lecture we will introduce real functions. So let us, given a subset A of the real numbers which is non-empty. A real function is a function f from A to R. In the following we present a number of properties that a real function may or may not have. The first one is the monotonicity. Now, there are four types of monotonicity. We say that the function f is strictly increasing if y larger than x implies that f of y is larger than f of x. Graphically, that means that if we move from x to y, we have a function that is just increasing in this way. So a function like this, but in general, a function like this, it is clearly a strictly increasing function. We say that the function f is weakly increasing if y larger than x implies that f of y is larger than or equal of f of x. So in this other situation we have that moving from x to y we may have a behavior like this, and this is weakly increasing. Then in a similar way we can define a strictly decreasing function if y larger than x implies that f of y is strictly less than x, and of course this is just say that moving from x to y we have a behavior like this. And finally, weakly decreasing if y larger than x implies that f of y is less than or equal f of x, with a behavior like this. Notice that two things. If f is strictly increasing, then f is also weakly increasing. In fact, the fact that f is strictly increasing is also included in the definition of weakly increasing. So f being strictly increasing is a sufficient condition for being weakly increasing. Instead, saying that f is weakly increasing is not a sufficient condition for having f strictly increasing. Right, so another property which is very commonly used in analysis and that many real function have is that of symmetry. We say that f is even if f of minus x is equal to f of x. And with this, we have in mind a function like this, for example. Clearly, this function can be mirrored with respect to the y-axis and nothing changes. We say that the function is odd if f of minus x is equal to minus f of x. And in that case, we would have a behavior like this. This is a typical behavior of an odd function. Notice that moving from x to minus x, in the first case we get exactly the same value. Instead, in the second case, moving from x to minus x, we get exactly the opposite value. As an exercise, let's prove that if f is odd, then we must have that f of 0 is equal to 0. Okay, let's give a proof of this. We know by definition that f is odd if f of minus x is equal to f of x, and this must be true for every x that belongs to the set A of definition. So in particular, this implies that if x is equal to 0, we should have that f of minus 0 should be equal to minus f of 0. But this is just like saying that f of 0 should be equal to minus f of 0, and this is possible if and only if f of 0 is equal to 0, which proves the original statement. Another property, periodicity of a function. We say that f is periodic if there exists at least one t larger than 0 such that f of x plus t is equal to f of x for every x that belongs to the domain of definition A. Now, every such t is called a period of f. Now, how does a periodic function look like? We can imagine something like this, for example. A function with a behavior like this is certainly a periodic function. So you see that, in other words, what happens is that the function repeats itself, and this is happening every period t. So let's see if a graph like this satisfies the definition that we have just given. In fact, you see that, for example, if we pick these elements, well, for 0 we get this value, and again every t we get exactly the same value. But I can do the same also if we go, for example, for this value here, and we add another t, we are back into the same value. So clearly this is a periodic function. Of course, we can also assume that the same value is achieved every multiple of t seconds. So for example, if we consider this value here and we jump ahead of 2t, we have this other value, and then same story on the for any other value. For example, if we consider this now, let me change color. Let's say this value here. Well, this is repeated exactly the same every 2t periods. So this is the meaning of period. So we can say that t, 2t, 3t, and so on and so forth are all periods of f. However, if there exists a minimum t larger than 0, it is called a minimum period of f. In this case, for example, clearly t is the minimum period across all possible periods that this function has. So in this case, this function has a minimum period. However, this is not always the case. In fact, there are some specific function, a little bit strange, but there exist periodic functions without a minimum period. I'll give an example. Consider this function f of x, which is equal to 1 if x is rational, and instead is equal to 0 if x is not rational. Okay, what is the graph of this function? Let's say that we have 1 here, we have 0 here. So if x is rational, we have 1, infinite many ones. And if x instead is irrational, we are all on the x-axis. So clearly, if we pick for every x, let's suppose that we pick an x here which is rational, then f of x plus t with t a rational number. Well, x plus t, if x is rational and t is rational, of course this is going to be this new number. This would belong to the rational as well. So we can say that this is equal to 1. And this is true for every possible t. If instead we will consider y that does not belong to q, is not rational, but again t is any rational number, then we can say that f of y plus t, well, in this case this new number here would be not in the rational. Okay, so that implies that f of y plus t is going to be 0. So you see that all possible rational numbers, all t larger than 0 with t rational, is a period. And so that implies that we are considering all possible t in the rational line. So clearly there is no minimum, period. For this function, still the function is periodic. Let's now review some elementary functions and try to classify these functions according to the properties that we have just introduced. Let's start with the simplest possible function, the identity function. F of x equal to x. The graph of this function is the following. Is simply a bisector, and it is easy to see this because if we pick any x, the image would be y equal to x. So clearly this gives rise to the bisector, and of course we are considering now this function to be defined from R to R. So this function is an odd function, and this is again easy to see because if we pick minus x, we have just minus x here. So we can check that f of minus x is just equal to minus f of x, and it is also strictly increasing. Second function is the power with the positive integer as the exponent. So we will consider f of x equal to x to the k. Now, of course, if k equal to 0, we just have a constant 1. If k is equal to 1, we have the identity. So let's consider now k larger than or equal to 2. So with k natural numbers. Now, if k is equal to 2, let me start with the k equal to 2. We have f of x equal to x to the square. And we know that the graph of this function is the following: x to the square. And we know that this function is even. In fact, f of minus x is equal to f of x. If we pick an x here, we pick minus x, of course this gives rise exactly to the same x squared here. Now, if we consider this function f from R to R, we know that this is neither injective nor surjective. We have already seen this in one of our previous lectures, but let's check it again. Clearly, because two different x are sent into the same image, this cannot be an injective function, and clearly we see that an entire part of the image, which is the negative real line on the y-axis, is not hit by any image of f, so that means that the function is not surjective. However, we can fix this problem if we consider f that goes from 0 plus infinity to 0 plus infinity, which is to say that we are now considering only the first quadrant, and we have this function now. So this is x squared, and now the function is invertible. F is invertible, and the inverse function is g from 0 plus infinity to 0 plus infinity, and we will define this function g of x as the square root of x. So this is important to say that this is a definition of the square root as the inverse. Now, what is the graph of the inverse function? Well, the graph of the inverse function, is this one. So we have x to the square here, and we have square root of x here instead. Now, clearly this point is 1 and 1. Now, to show that this is indeed the graph of the square root of x, I will prove now a general theorem, and this general theorem is the following. The graphs of a function and its inverse are symmetric with respect to the bisector. Now let's prove this. So this is the bisector. Okay, and I'm saying that the two graphs are just the mirror image of the other. Okay, so let's give a proof of this theorem in the most general case, and then we'll come back on the specific case of the x squared. Let's say that we have a function that has a graph like this. So this is f of x, and we pick any point x. Of course, this will be the two coordinates of this point. Now let's pick the graph instead of f to the minus 1. Okay, f to the minus 1 of x. Well, now what I'll do is basically looking after the point that has y coordinate equal to x, and we know that because this is just the inverse function, its x coordinate is going to be f of x. Now, what I would like to prove is that these two graphs are symmetric with respect to the bisector. Okay? Now, proving these things amounts to proving basically two things. So, first, we need to prove that the middle point of the segment connecting, let's say that this point is A and this point is B, A and B lies on the bisector line, which is to say that this segment, let me take another color, yes, let's say that this segment, the middle point should sit right in on the bisector line. And the second thing I need to prove is that the slope of AB is -1, which is to say that the segment AB is perpendicular to the bisector line. Okay, so let's start with the first one. Let's start with the first one. So the first one is that we need to find basically the middle point. Let me call this middle point M. But this middle point M, if we look after the coordinates of this middle point, we see that clearly the x coordinate of M will be right in the middle between x and f of x. So x plus f of x divided by 2. And the y coordinate is again x plus f of x divided by 2. But clearly these having the x and y coordinates equal one to the other, that means that this belongs to the bisector. Good. So first condition met. Second condition, we need to find the slope. Okay, how do we find the slope of this segment? Well, we just need the slope of AB will be just the ratio of the difference between the y-axis and the difference between the between the y coordinates and the difference between the x coordinates, right? So if we do this, we say yb minus ya divided by xb minus xa. Okay, but yb is x, ya is f of x, and then xb is f of x, x of a is x, so clearly this is -1. So this finally proves that yes, every time we have a function f of x and we build the inverse function f to the -1, these two graphs are one the mirror image of the other with respect to the bisector line. So this explains the graph of the function square root of x being exactly the mirrored image of x to the square with respect to the bisector line. Good. Let's add a note here. This is very important. The roots of with even indices take as input only positive values and x larger than or equal to 0, and give as outputs only positive values y larger than or equal to 0. So what I'm saying is that because we have restricted in this specific case x to the square, we have restricted x to the square only to this part, to the positive x-axis. We have the square root of x, which is the inverse, of course, that needs to be limited only to the first quadrant. So this is important to say that it's not possible, of course, to if we, for example, write square root of 4, this is just equal to 2. It cannot be square root of 4 equal to minus 2. This is totally wrong, because the definition of the square root of x is something that is referred only to the first quadrant. Right. Now, as a further example on the function f of x equal x to the square, let's try to prove that, f of x equal to x to the square is strictly increasing, which is of course something that we clearly see from the graph, right? So we see that this function, just looking at the graph, we see that this function is always increasing, but we want to prove this formally. Okay, so we can give two proofs. Okay, proof 1, and then we'll give another proof. Okay, proof 1 is that if y is larger than x, okay, if we pick y larger than x, so that implies what? We should like to prove that f of y is larger than f of x, right? So this is the definition of strictly increasing, which is to say that y to the square is larger than x to the square. Okay, how can we prove this? Well, if y is to the right of x, we can also say that y is equal to x plus a for some a larger than 0, right? So in other words, we are saying that this is a larger than 0, which is the increment passing from x to y. Now, if we replace this in this expression, or basically if we calculate f of y is y to the square, but that means x plus a to the square, which we know is x to the square plus 2 times ax plus a to the square. Now it turns out that of course this is larger than 0 because a is larger than 0, and this can be larger than or equal to 0 because we also considered the possibility that x might be 0, but in any case this will be larger than x to the square. So this proves the fact that f of x is a strictly increasing function. But we can provide also another proof of the same fact. Okay, so remember that we would like to prove that y to the square is larger than x to the square if y is larger than x, right? So we can rewrite y to the square as y times y, okay? By one of the ordering axioms, which is in particular OP, okay, remember the OP axiom on real numbers, we know that this is larger than y times x because y is larger than x. But again, reapplying OP, we have that this is larger than x squared, which finally proves the assertion. Okay. Now, at this point we know that we know that f of x equal to the x squared is strictly increasing. And that also proves that the function is injective. In fact, if we look again at the graph of the function x squared, injectivity means that for every possible horizontal line we cross the graph only once, and this is exactly what happens. For every strictly increasing function, we know that that proves the injectivity of the function itself. Uh, uh, we know also that f of x is equal x squared is also surjective. Remember that we are limiting f from r from only 0 plus infinity to 0 plus infinity. Well, in this assumption, we know that we can hit every possible real numbers on the positive y-axis. So yes, I mean, at the intuitive level, we see that the function restricted in this way is surjective, but formally this should be proved. Okay? Now, final consideration is that what we have said, what we said for k equal to is valid in general for all k for even k belonging to the natural numbers. The only difference is that what happens is that the functions, what is the general behavior of the function? Well, if we start with the x squared, this is x squared, let's say that this is the point 1. Of course, we know that we end up in 1. If we increase the exponent to the next even natural number, we have a behavior like this. So this will be x to the 4th. And if we keep increasing this, for example, to x to the 6th, we have a deformation of the curve, which is getting closer and closer to the last basically in the limit, this will be the behavior of the function is just the rectangle with the base lying on the segment minus 1, 1 of the x-axis. Okay, so this is in the limit. Let's now pass to consider instead powers with odd exponents. For example, let's consider f of x equal to x to the cube. Okay? Now, the graph of this function is the following. And we immediately So this is x to the cube. We immediately realize that this function is odd. In fact, if we have x here, we have x to the cube, which is exactly the opposite of the image of minus x. So once again, we have that f of minus x is equal to minus f of x, which proves that the function is odd. And it is also strictly increasing, which implies that it is injective. And from the graph, we also realize that every possible element on the y-axis is hit by an image. So we can also say that the function is surjective. And when I'm saying this, I'm considering f from the entire R to the entire R. So that indicates that f of x equal to the x cube is invertible. And the inverse function, is g from R to R, and we will represent this function as the cube root of x. And this is another definition of the cube root of x. And by applying the previous theorem, we know at this point what will be the image, the graph of the inverse function, because we will just rely on the idea that it will be the symmetric with respect to the let's say that this is the bisector. Well, at this point we know that this would be the cube root of x, which is the symmetric image of x to the cube with respect to the bisector line.